friends, I am Assist. I welcome you all on my YouTube channel Engineering Made Easy. Today I will discuss optical fibers. In this video I will tell you many important points about optical fibers. These points will cover lots of information about optical fibers and help you in understanding what are optical fibers. In this lecture I will discuss many points like what is an optical fiber, its structure and working principle, optical fiber communication process, and various types of optical fibers. We will also discuss the benefits of optical fibers, various losses in optical fibers, and also the dispersion in optical fibers. I will discuss every point later in detail in separate video lectures. So first of all, let's start with what is an optical fiber. So an optical fiber is a flexible and transparent fiber which is made by drawing glass, which is called as silica or plastic. Okay. The optical fibers have a diameter slightly thicker than that of a human hair. So this is clear by the definition that it is a flexible and transparent fiber, and these are made by stretching the plastic or silica. Okay, so now discuss other points like structure and working of optical fibers. So optical fibers are made of glass, as we have discussed, or plastic, and are very thin. And most optical fibers used in communication have a diameter of 0.25 mm to 0.5 mm, okay, including the outer coating. Actually there are three layers in total. First one is the core, then the cladding, and the outer coating. So including that outer coating, its thickness, its diameter is 0.25 to 0.5 mm. Okay, and optical fibers, as I told you, have a transparent core. There is a transparent core, and over this core there is a transparent cladding. Another layer is also there, which is called cladding, and over this cladding we have a protective covering to protect it. Okay, we will discuss what is a core and what is cladding and how it is covered using the protective covering. So let's proceed. Okay, so we are here studying the structure and working principle of optical fibers. So here it is written that based on refractive index profile, there are two categories of optical fibers. We have categorized them in two categories, okay, based on the behavior of refractive index, how the refractive index varies. Okay, so first type is the step index optical fibers. Okay, step index optical fibers, and another is the graded index optical fibers. So what are these two? Let's understand each of these. Actually, in step index fibers, the refractive index profile makes a step change at the core cladding interface. As I told you that there is a core. Let's see the structure. Actually, first let me show you. Okay. Can you see this? Okay, here you can see it. Yes, this is how the optical fiber looks like. In this, as I told you that there is a core inside. Okay, so this is a core, okay, this in blue, and this green colored layer is cladding. So I will discuss what is happening here, but just to tell you the structure. So there is a core, and over this I have cladding, and these have different refractive indexes. Mu1, its refractive index is mu1 of the core, and cladding has mu2 refractive index, and these are rated as mu1 is greater than mu2. How it is, why it is done, I will tell you. So the light ray propagates inside the core. Okay, so let's again come to our topic. This step index fibers. So in step index fibers, the refractive index profile makes a step change at the core cladding interface. I have shown you the core cladding interface where the cladding and core touches each other. So where it is the place where they make step change. Step change means sudden change. Since in core it has mu1 refractive index, and outside the core it has cladding having mu2 refractive index. So it makes sudden change from mu1 to mu2. In step index fibers, if core has refractive index mu1 and cladding has refractive index mu2, then mu1 is greater than mu2, as I have told you, and this is responsible for total internal reflection. You know total internal reflection, TIR, in optical fibers. So how does it take place, how it happens, we will see it. Okay, so this was the case of step index fibers. Now we will discuss what are graded index fibers. Okay, while in graded index fibers, okay, while the graded index fibers don't have a constant refractive index in the core, as we have seen that in step index fiber we have mu1 as the refractive index inside the whole core, but it is not so. It varies inside the core in case of graded index fibers. How it varies? The refractive index of the core decreases with increasing the radial distance from the core. As we move away from the axis of the core, okay, from the axis of the core, it keeps decreasing. As we move radially outward towards cladding outer surface, then it slowly goes down. Okay, it decreases, the refractive index decreases. It has maximum value of the refractive index at the core axis, obviously, so it will have maximum at the core, but the refractive index of the cladding is constant. The cladding refractive index does not vary, it is constant. So now let's discuss the total internal reflection that takes place inside the optical fiber. The light rays travel inside the core by the phenomena of total internal reflection, TIR. Actually, the light rays that propagate through the optical fiber do not enter into the cladding. They are confined to the core only, and they travel with the phenomena of total internal reflection. It takes place inside the core, okay, at the core cladding interface. Since the core has a slightly refractive index higher, okay, than that of the cladding, since I have told you that mu1 is greater than mu2, so when the light rays fall on the core cladding interface, means moves from denser to rarer medium, it returns back into the core. Did you get the concept? If not, I will tell you. Because when light moves from denser to rarer medium with an incident angle greater than the critical angle, it comes back into the same, means the denser medium, back to the same denser medium. So how it takes place, I will tell you. Listen, here this is a just suppose that here it is cladding and here it is core. As mu1, it has mu1 and it has mu2. This is if it is mu1 and here it is mu2, and we also know that mu1 is more than mu2. So when light rays move in this way, it is moving from core, it is in core, then it try to goes into the cladding, okay, but it is totally internally reflected. TIR takes place at this interface of core cladding and at this interface. But how does it take place? Here we have denser medium and here we have cladding's rarer medium. So suppose here is the cladding rarer medium having mu2 and here is mu1, and when the light ray moves from this core to this cladding, like here from core to this cladding, it moves, okay, and at this point, at this interface of core cladding, the refraction phenomena takes place, okay. The refraction takes place at this point where the mu changes, refractive index or the density of the mediums changes, and when we know by the law of refraction in optics that when any light ray travels from denser medium to the rarer medium, and here it is the normal, we have the imaginary normal perpendicular, so it moves away from the normal, okay. Means if it is theta 1 and here if we have theta 2, then in this case theta 1 is less than theta 2, it moves away. If it would have been the opposite case, then if it moves from rarer to denser, then it would have come closer. So in our case we need only this concept, so it moves away, okay, from the normal when it enters into the rarer medium. And suppose if we keep on increasing this theta 1, okay, then it will theta 2 will also increase. So at some point we will have a theta critical point which is obviously larger than theta 1. So this theta 2 will keep on increasing and this ray of light will move parallel to this interface surface of core cladding or these two mediums, okay. So in this case this theta, this incidence angle would be called as the critical angle, where the other part goes along the surface, okay. So this is the case of critical angle. But what happens when we keep on increasing this theta c also? If I increase this theta c more, then the total internal reflection takes place. Just imagine that if I keep on increasing this angle, then this angle will also increase, and at this point it is at this. If I keep on increasing it more than theta c critical, then it will come back into this same medium, denser medium. So you can understand it here that theta r, this theta r is the angle which is more than theta c, so it will come back into the same denser medium, okay. This is the total internal reflection, because here there is no reflection. Actually it seems like a reflection. It is a reflection of wave having these two angles equal and the normal, okay. These two angles, angle of incidence and reflection, are same. So this is totally internally reflected. The light ray is completely reflected back into the same medium. That's why called as total internal reflection. So it is reflection here, okay. So understand the concept here. In the same way, here we have the denser medium and the rarer medium of cladding. When light ray moves from this denser to rarer, it, instead of going in this medium, since this theta here is more than the theta critical, since here this theta is obviously more than theta critical, so the TIR takes place, total internal reflection takes place. So it moves into the same medium, it goes in this direction and moves into this medium. Again at this interface same phenomena happens, it moves inside this medium from it is rare, and this takes place. This keep on moving in this way with the total internal reflection, TIR. I think you got the concept. Now let's see few more points. The optical fiber communication takes place between 0.8 micrometer to 1.7 micrometer. Keep this range in mind of the wavelength of electromagnetic spectrum. In the electromagnetic spectrum, it takes place in this range, in this wavelength range, this optical communication. Okay, so now we will discuss the optical fiber communication process, how the communication takes place with the help of optical fibers. How can we send the message from the transmitter to the receiving end with the help of optical fibers and other few more components. In this, the message that we want to transmit may be non-electrical in nature. Suppose maybe audio signal, our message signal, our voice speech signal. So first of all, it needs to be converted into electrical form using transducers. So transducers are what? Transducers are just the energy converters. They convert energy from one form to another. So we need to first convert this non-electrical nature, having non-electrical signal, into electrical signal. When it has been converted using the transducers into electrical signal, then the message is converted into electrical form. Now the message which is converted into electrical form, it modulates an optical source. Optical source means we can take lasers or LEDs, light emitting diodes. Okay, so we use in optical fibers mainly lasers or LEDs as the optical source. So this message is modulated. This message is we modulate this message over this light, okay, that comes from the optical sources. So we have modulated light signal having message. Okay, after this, the light rays which contain the message travel through the optical fiber, okay, by the phenomena of total internal reflection, as we have studied. Okay, due to TIR, total internal reflection, the energy loss is negligible inside the fiber while traveling. That's the beauty of optical fibers, that there are negligible losses, as total internal reflection has no loss, almost ideally no loss, because it gets totally internally reflected, so no part escapes. Ideally, actually, in practical there are some issues. We will discuss also the losses that are faced, but ideally it is negligible or zero. Now at the receiving end, okay, it is traveling. Now at the receiving end, the photodetectors like photodiodes or phototransistors, etc., are used to convert the light signal back into the electrical signal. At the receiving end, since we have the light rays, so we need some mechanism to first, since we want to retrieve our electrical signal back, so first of all we need to convert this light rays, these light energy, into electrical. So we can do this using the phototransistors or photodiodes. These are the devices used at receiving end that are light sensitive to light, that can produce electrical signals and are stimulated by and are very sensitive to light or photons. Okay, so these convert it back into the electrical signal. Then the original message signal is retrieved from this electrical signal. Since the original message was, if it was in non-electrical form, maybe audio, then it is retrieved from this electrical signal back into the original form. Now let's discuss various types of optical fibers. So we will discuss the optical fibers here based on the modes of propagation. Okay, so there are two types of fibers based on the modes. Modes means the various paths how the light ray moves inside the optical fiber, there are various paths. Okay, so propagation paths. Based on propagation paths, there are two types of optical fibers. These are single mode fibers, SMF, and multi-mode fibers, MMF. Okay, this is the short form, multi-mode fiber, single mode fiber. So single mode fiber, let's understand what are these. As clear by the name itself, the single mode fibers SMF supports only one propagation path, since they have very small diameter. Okay, these single mode fibers have very small diameter, so it is not possible for many light rays to travel through it. It is so small in diameter that we can have only single ray of light, only one propagation path through this optical fiber. They are so small, so that's why it is called as single mode fiber, because it supports only single propagation path through the fiber. Okay, while in case of multi-mode fibers, we can understand it that it can support many propagation paths or the transverse modes, as they have larger diameter. Because of larger diameter, it is possible for multi-mode fibers to support many transmission paths. Lots of light rays can travel through it. Okay, which is not possible in case of single mode fibers. The single mode fibers SMF are used for long distance communication, while multi-mode fibers for short distance communication. Because there are less losses are very less in single mode fibers, because there is less dispersion, less interference there is no interference in case of single mode fibers. There is no intermodal dispersion, means since in case of multi-mode fibers, we have lots of light rays. Various light rays propagate simultaneously inside the core, so they interfere with each other, they broaden. We will see it in dispersion topic, how the broadening of the pulses, light pulses, takes place as they move through the optical fiber, since it is not possible in case of single mode fibers, because there is only one mode of propagation. So it is used for long distance communication because of less losses. The single mode fibers provide greatest transmission bandwidths and lowest losses in the communication. Not only lowest losses, but also it provides the largest bandwidths, the single mode fibers. Okay, so keep this in mind. Now the fifth point is the benefits of optical fibers. Here we will discuss various advantages of using optical fibers. It is, energy loss is negligible inside the optical fibers while propagation due to total internal reflection. We have discussed it. TIR has negligible losses. Optical fibers provide very large potential bandwidths. Okay, since optical communication takes place at a very high frequency, this frequency is 10 to the power 13 to 10 to the power 16 hertz. Because of this, since when any range that any electromagnetic spectrums waves that are having very high frequency are used for communication purpose, then they can provide larger bandwidth. It means higher the frequency range, higher would be the bandwidth. Since optical communication takes place in this high range, so it can provide higher bandwidths. Higher bandwidths means large data carrying capacity. Okay, the optical fibers have a small size, we have discussed it, are lightweight and very flexible. Okay, these are just a few properties. Okay, few more advantages of optical fibers are: optical fibers provide electrical isolation and are shock resistant, since inside the fiber light propagates, not any electric current. We have seen that in optical fibers only the light ray propagates. Okay, using the total internal reflection, there is no chances of any shock in case of electrical fibers or in case of optical fibers, but in case of metallic wires we know that electric current flows. So it is also one more advantage. Optical fibers provide high degree of signal security. How? Since these fibers do not radiate significantly, unlike copper cables. Copper cables radiate, okay, they do not radiate. Okay, so the chances of loss or stealing of the security is, breaking of the security is not easy. Optical fibers are easy to maintain and the communication system is also reliable. You can easily maintain them. They are quite rigid and tough. So the system is also very reliable. Now the sixth point of our discussion is losses in optical fibers. Now we will discuss what are various kinds of losses. As I have told you that although the optical fibers have negligible losses while propagation, but still there are some losses, although maybe very small. But what are these losses? These are the following. First is the material absorption. Second one, the linear and non-linear scattering. And the third one is fiber band losses. Actually it is not possible to cover all these things in detail. We will have separate lectures for discussing each of these and also many other points that we have discussed. So it is good to know the points only in this lecture. Material absorption, the material used in the construction for optical fibers absorbs some energy, absorbs some light energy. And linear and non-linear scattering of the light rays also takes place linearly and non-linearly. So then the third one is fiber band losses. When there is some band, we cannot have long distance communication without bending the fibers because of the path. We need to bend it somewhere. So if there is some bending in the fiber in the communication process, then there would certainly be some losses. Okay, we will discuss in separate lectures, don't worry. The seventh point is dispersion in optical fibers. The last point, it is our last point. What is dispersion? So when light rays travel through fiber, the phenomena of dispersion is just the broadening of the transmitted light pulse. Because of this dispersion, each pulse broadens and overlaps with its neighboring pulses. We have discussed it. So when many pulses travel through the optical fiber, as they travel along the way, it keeps on broadening. These pulses broaden and they spread, and they just overlap with the nearby pulses that are moving simultaneously with these pulses. So they overlap with each other. Okay. Due to this, the pulses become indistinguishable at the receiving end. At the receiving end, it becomes difficult to identify these pulses because of their mixing or because of their overlapping. Okay. This effect is known as intersymbol interference, ISI. We call this overlapping due to broadening of pulses as the intersymbol interference. This is a phenomena of intersymbol interference. So this is the dispersion which is found. Okay. Now few points about dispersion are: the dispersion is of two types actually, intermodal dispersion and intramodal dispersion. In intermodal dispersion and intramodal dispersion, we will deal each of these. Just this is between many modes. Intermodal means between the modes, various modes of propagation, and intramodal dispersion means within the same mode. Okay, just keep this in mind. We will discuss it later. So here is the comparison of intermodal dispersion in different types of optical fibers. Since we have studied many fibers, multimode fibers, and based on modes, multimode and single mode, and also the graded and step. Okay, so how is the comparison between all these based on the intermodal dispersion? So the intermodal dispersion is maximum in case of multimode step index fibers. Okay, step index fibers which supports various modes is called the multimode step index fiber. Then it is lesser in case of multimode graded index fibers. Okay, and it's still lesser than this in single mode step index fibers. Okay, so friends, these were some important points about optical fibers, and these points will help you in getting the overview of the optical fibers. I hope you might have found this useful and interesting. In my next video lectures, I will cover these all topics in detail in separate lectures. Okay, so friends, you should like and share the video if you found it useful, and please don't forget to subscribe my channel, Engineering Made Easy. Thank you for watching. Bye bye.